Okay, calculus, let's talk more about planes, three-dimensional planes, or two-dimensional planes in three-dimensional space. If two planes are parallel, they're either on top of each other and intersect everywhere, or they are a certain distance apart, which means they intersect nowhere. Every other set of planes will cross each other and intersect at a line. So we can determine the angle between two planes by determining the angle between the two norms to the plane, because if the two planes are, say, 30 degrees apart, the norms, which are orthogonal to them, should also be the same 30 degrees apart, as pictured here to the right. This means we can use the equation for angle between two vectors, because the norms are vectors, which means we can use some rules we previously did, where the cosine of theta equals the absolute value of n1, the dot product of the two norms, divided by the magnitude of the two norms. So let's do that in a problem. Find the distance, or find the angle between the two planes, x minus 2y plus z equals 0, and 2x plus 3y minus 2z equals 0, and find the parametric equations of their lines of intersection. Okay, so we know the norms here are just the vectors for each of these two planes. So the first norm is 1, negative 2, 1. The second norm is 2, 3, negative 2. So we know cosine theta equals the absolute value of the dot product of norm 1 and norm 2 divided by the magnitude of norm 1 times the magnitude of norm 2. Okay, so let's check their magnitudes real quick. The magnitude of norm 1 equals the square root of 1 plus 4 plus 1. We get those by squaring each term. The magnitude of norm 2 is the square root of 4 plus 9 plus 4, which is 17. So we have the square root of 6 times the square root of 17. And let's do the dot product. The dot product of n1 and n2. 1 times 2 is 2. Negative 2 times 3 is minus 6. 1 times negative 2 is minus 2. 2 and negative 2 cancel, so this is just negative 6. So we're going to take the absolute value of this. So cosine theta equals the absolute value of negative 6 over the square root of 6 times the square root of 17. So this is 6 over the square root of 102. Is equal to cosine theta. Now to find theta, we can take the cosine inverse of 6 over the square root of 102, which is in radians 0.9346 radians. Now, that's also the equivalent of 53.55 degrees, but that's not the only thing we were asked to find here. It said, find the parametric equation of their lines of intersections. So how can we do this? We've got our two equations, and we've got to have something else in order to make this work. Well, normally when we have two equations, we'd like a third one because they're in three variables. But we know that this line is going to have a relationship with x, y, and z, so we only really need two of those. If I multiply the first equation by 2, for example, and add it to the second equation, I get 4x. This will be minus 4y plus 3y. So that will be minus y. My z's cancel to get 0. If 4x minus y equals 0, that just means y equals 4x. I can do the same thing. If y is equal to 4x, I can plug that back in to any of my equations to get an equation for just x and z. So if I plug it into the first equation, I get x minus 2 times 4 is 8, minus 8x plus z equals 0, which means negative 7x plus z is 0, so that means z is 7x. So we've got x, y is equal, we have an x, y, z. But y is equal to 4x, z is equal to 7x. So we have x, 4x, 7x. Now what can we do with that? Well, this is a vector relative to time. So we could use it combined with our starting point. We don't have a point, but we can just say it's 1t for x is t. So y is 4t and z is 7t. Now, another way you could have done this and got the same vector is if you did the cross product of our two original vectors, you would have gotten the same thing. So here's a systems of equations way of doing it, and there's also a cross product way of doing the same product. Okay, so let's consider two types of problems involving distance and space. It's not too hard to find the distance between a point and a line, but we can also find the distance between a point and a plane. Now, the distance between a point and a plane is the length of the shortest line segment connecting the two. The distance between a plane and a point is the magnitude of the projection of the norm, or projection of PQ onto the norm, which is the absolute value of the dot product of the PQ vector and the norm divided by the magnitude of the norm, where P is a point in the plane and N is normal to the plane. So let's do one problem with that first. Let's rewrite. We know the distance is equal to the dot product divided by the length of the norm. So find the distance between the point 1, 5, negative 4 and the plane 3x minus y plus 2z equals 6. Now, we need the norm here, which is just the coefficients for our x, y, and z. So 3, negative 1, 2. Got a point. We need a vector from something in this plane to this point. So how can we do that? I just need to find any point in this plane. So I can just let two of these variables be 0, and that would be easy enough. So I'm going to let y and z be 0, so 3x equals 6, which means x equals 2, so that's the point 2, 0, 0. And that gives me a point P, and this is my point Q, so what's my vector from 2, 0, 0 to 1, 5, negative 4, and of course you can pick any point. The distance here would be 1 minus 2 is negative 1, 5 minus 0 is 5, negative 4 minus 0 is negative 4. So I need to do the dot product of negative 1, 5, negative 4, and 3 with negative 1, 2, and divide it by the length of my norm, which will be the square root of these three things squared, added together. My dot product should be negative 3 minus 5 minus 8 divided by 3 squared is 9, 1, 4, so the square root of 14. So this is the absolute value of negative 16 over the square root of 14, which is 16 over the square root of 14, which is approximately 4.28, which means the closest that point gets to the plane is 4.28 units away, depending on what the unit is. And that's all for this video.